The third author in this paper is Liu, but I misspelled this Y. That should be a YI on the end. He just finished his PhD at the University of Bath, and so some of the stuff I'm going to talk about toward the end is really out of his thesis. This talk is really kind of a compilation of several papers with some new work at the end. It's really about the sort of history of black smoke monitoring in the United Kingdom. And so I'll include a case study demonstrating that when administrators are left to their own devices, they'll tend to put sites for monitoring pollution where the pollution levels are high, and that kind of makes sense, right? Except if you're a statistician, you realize that you need contrast for fitting models, and so that's not a good idea. So there's evidence that the preferential selection was made, and then the question is, what do you do about it? And so this talk will give a couple of approaches that we've taken to try and adjust for the bias that this selection process introduces. This is kind of the main slide in some sense. It gives a kind of summary of the story. It really started, I think, the project itself started at SAMSI with a one-year, let's see what they call them, theme year on spatial statistics with applications to environmental epidemiology. And that's been a very stimulating group that's produced quite a number of papers by different people. Bullet point number 2 describes the effects of this preferential sampling, where sites are actually deliberately chosen to be where the pollution levels are thought to be high. And so in the first part of this is where you're reporting trends and official statistics. And so if you put the stations where the levels are high, of course your results are going to be sort of biased upward. And so it's not surprising that if you impute the overall average annual mean for the whole country, it's going to be too high. And likewise, the number of sites in the country which are out of attainment of the regulatory standards will be too high. It'll overestimate the number of sites that are out of attainment. Regulators will say that doesn't really matter because we really only care about the sites themselves. We don't care about all the places that were not monitored. But I think citizen scientists will probably find that argument somewhat objectionable. They're going to be interested in what happens at the school or at the local hospital area and so on. And so they'll really want these averages and trends to say more than just what's happening at the sites. You get into really deep water when you get to estimating health effects, because surprisingly, if you are biasing the levels upward, you have to reduce the estimated health effects, okay, to make the model fit. Because the number of deaths is not going to change on the left-hand side of the equation. And the fact is that at least in the United States, the Environmental Protection Agency does their risk analysis by looking at the literature in environmental epidemiology, and it finds the relative risks that are actually calculated by epidemiologists, and it uses that in the risk assessment. So if you really wanted to reduce the number of deaths, for example, you would use the estimates that the epidemiologists have produced. And so you say, okay, let's hypothetically reduce the levels by maybe 10 micrograms per meter cubed. Let's calculate how many deaths would be that would mean we reduce. But of course, if you've misestimated too low, you'll say, if we really want to reduce the number of deaths by, say, 10%, we actually have to reduce the pollution a lot more to get down to that level. And industry has long complained about this effect, and in fact has sued the EPA with some regularity, claiming that they've misestimated the health effects in this way. And I think, so the talk really is about how you might adjust these biased samples. And so that's I think the main takeaway stuff. And then the rest is going to be a sort of summary of the things that we've done. So the big story really was the famous 1952 London fog that you all know about. Black smoke, I guess, was involved there in helping produce the fog, and unquestionably it led to thousands of excess deaths in just a few days. You didn't need to be a statistician, I gather, to know that fact, and so it led then inevitably to some change. And in this country has been amazing in the way it is contended with that, and the way it actually then went on to clean the air and so on. The Clean Air Act here was in 1956. The US one was in 1970. And that's the one I've been more familiar with and worked with. Air quality standards were imposed, black smoke levels went down in this country, and then the need to monitor declined. The monitoring is expensive, believe me. And not only the initial installation, but you have to manage the monitors, right? So it's quite expensive. So of course, lots of these sites were actually shut down. And the question is, how were they shut down? By what method? Well, come to that in a sec. But here's a graphic that shows rather dramatically how much things went down. And on the left-hand side, you see sort of a spatial graphic which shows the higher levels back in 1966 and moving on down to 1996. You see a fairly dramatic decline across the country. And here's the overall averages, which in the screen plot, which shows them going down as well, which you might expect. This plot really says it all. It sort of describes 4 different classes of sites. The way back here in 1966, they were almost all in. Some were added later. But the point of this graphic is that the green ones were mostly terminated as time went on, and that's reflected in the fact that these bubbles get smaller, because the bubbles represent the number of sites. Okay. So the green ones at the bottom, these are the ones where the pollution was low. They were terminated, and there were some sites here that were added and then terminated because the pollution levels were not so high. And then there were other sites which were added and kept, and some that were just kept from the beginning. And those are the ones that had higher levels. And we did a formal model fitting analysis of this, and this is a key feature. I should add, since I see Peter Diggles here, that his paper, the one he published with his colleagues, that really has stimulated interest in this whole subject of preferential sampling. That was 2010, I think, right, Peter? It's generated a lot of interest, and so this is building on. But the difference in our analysis is that we actually modeled time. We put time in, and that gave us a way of looking at what happened over time. And so this is a hierarchical Bayesian type of model, and it shows a kind of quadratic decline in the level of the logarithmically transformed BS pollution level. And rural and urban effects are still in there as a significant predictor. And then the groups, the 4 groups, are distinctly different, formally speaking. Anyway, the main message here is that there were two different collections, as I said before. There were the sites that were non-retained. That means they weren't in at the end because the pollution wasn't high enough. And then there's the blue ones where they were kept in to the end because the levels were fairly high. I'll sort of skip over this slide. I just wanted to say that we had to rely on in-law. We couldn't run MCMC because there's an awful lot of, this is a high dimensional data problem because of the correlation amongst the sites and over time. And so we eventually relied on in-law and this approximation technique for approximating the stochastic models. And so Peter, you made the point in Seattle that the in-law does have limitations, and thank you for that. I think Finn Lindgren says he's trying to address that problem, but anyway, that's an aside. Air pollution monitoring should be, we think, should be giving a representative sample, because once the data are out there, they will be used, sometimes quite uncritically, by people for all sorts of other purposes. And the epidemiologists have used them pretty much uncritically in calculating risk effects. So for epidemiological studies, policy development, and the assessment of attainment of regulatory standards, it seems to us that these things should be and that the stations should be cited to make the results more representative. Well, now, failing that, is there anything you can do about it? And that's what this talk's really about. It's kind of a short version of what we've tried to do in a couple of cases. So we've looked in particular then at these two cases. One is about the production of official statistics, the kinds of things governments publish to show that there's been a trend, a favorable trend. And then the other part is about health risk assessment. And that's the part where, as I said before, it's really important to get those health risks right, even for the regulators, because they use them in actually calculating the benefits of various scenarios for reduction in pollution levels. So thinking of it from that perspective, we actually used a superpopulation, finite population kind of modeling approach, and the Horvitz-Thompson estimator, which has been a classical way of correcting for bias in survey sampling. And so if you use for the superpopulation a likelihood model, a likelihood-based analysis, you'll get an estimating equation, right? And these y's will be the actual pollution levels, some of which are seen and observed and some not. And then in this equation, what we have is just the sum over the sample sites, the ones that were monitored at time t, and we put in the survey weight to adjust this estimator that you get from solving this equation so that it is sort of unbiased, at least under the superpopulation model. The pi that you see here is the probability that site U is included in this set of sites that are included at time t. It's the probability that the site U is included in the sample, given all the previous data. Okay. And so that's the basic approach we used. And so everything would be fine, except, of course, unlike the classical survey sampler, we don't have any good way of estimating the pi's, the survey weights. So what we did then is we estimated them by going back to the superpopulation model and using that to motivate an analysis and a time series analysis to get the estimates. So there are two ways we could have done this. The first way is the hard way, and we haven't really done anything much with this. But here we would see the samples, the sites that are selected as being in themselves a time series of sets. And we model that. For the work we've done, we cheated, and we actually used a logistic regression analysis to compute those pi's. And so this was fairly simple and reasonably easy to do from a computational point of view. But this is definitely one area in which this work certainly could be improved. Okay? So what you're doing now is going year to year, and you're checking to see the ones and the zeros in a logistic modeling framework. And so you're using your logistic model now. You're actually using an AR1 kind of logistic model, which looks at the last year to see what choices were made in the next year by the regulators. When I say regulators, of course, I'm talking about a really complicated administrative structure for picking these sites. And in the United States, this involves mayors of towns, and it involves committees, and it involves bureaucracy and definitions and how far away from a highway and all manner of things. How many sites in a city? So there are like maybe 10 in my city, my metropolitan area, Vancouver. No, that's not right, 17 in the big area. And so those got placed somehow by some people, but nobody knows how, it's never recorded. And so what we've done now is laid on a statistical model, much in the same spirit as Peter did in his paper, and then tried to explain with this statistical model what was actually done. Anyway, once we've got the pies estimated, we can now estimate population averages, and by making the y's binary in this equation, or in this estimator rather, by making them binary, ones and zeros, we can also estimate the number of sites across the country which were out of attainment. This is over all the country, the sites that were monitored and the sites that were not. And so you can see that it makes quite a dramatic change. This is sort of the plot you saw before about the overall average. And so the blue is the overall average that you would be plotting if you ignored the preferential sampling. But if you take account of the logistic modeling and all that, Horvitz-Thompson, you get the red one. And so as you can see, there's really quite a big drop in the level. This is micrograms per meter cubed, and this is back on the original scale now, not on the log scale. And so we're at 50 micrograms per meter cubed. This is the average across the country. And so this is dropping down. And so this Horvitz-Thompson is showing you that in some places the actual levels, our estimated level is about half of what the uncorrected estimate would give you. And on the right-hand side is the number of cities out of attainment, the number of areas out of attainment, sorry, the number of sites that are not in attainment. And once again, the red is quite a bit lower than the blue. Okay, so to wrap up, I'm going to talk just briefly now about the newer work, which is not published, and this has to do with the health effects. This is the one, as I said before, that I don't think the regulators can wiggle out of. This is a problem for them too. And by the way, I haven't done this analysis, I haven't attempted yet the analysis for any place in the United States. It just so happened that my co-author, Gavin Shaddock, had this data set for the UK, and that's how we got started. But it's of interest, of course, in its own right. So when we're looking at, in this case study, we're looking at respiratory morbidity. Okay? And we decided that we would look just at the years 81 to 84 when you saw that really dramatic difference in the Horvitz-Thompson estimates. So these are the mortality rates combined over the 3 years. And then for exposure, we're looking at the estimated levels in the 77 to 80 period, at 3 years before and 3 years after. So this kind of smooths a bit over the 3-year period. And the covariate was the binary rural-urban indicator that we had in the previous slide. So what we did then was to go back to these two sorts of sites. There were the sites, the red sites where the pollution was low, and there were the blue sites where the pollution was high. The thing is that the health counts were based on administrative data and represented wards, what you call in this country wards. And so we had to then move the analysis up to the ward level, and we did that by going through each ward and taking the average level of pollution level in that ward, okay? So the red wards are the ones which had almost all G1 sites, that is low level. The blue ones had mostly G2 sites, high level, and a few G1 sites, okay? So now we've taken the original G's and replaced them by W's, and that's where the analysis will begin. But before going that, we refitted our original model, where now we have a G1 and a G2 in here to represent the two classes of sites. And this model is at the site level, so it's allowing us to impute missing G1 values. Because remember, a lot of those sites dropped out, so we can now impute them with this equation. But the same equation can also be turned around, since its coefficients and so on depend on the spatial location. We can actually then also impute values to the blue sites by simply changing the predictor to what it would have been had it been in the red category. Well, why would you want to do that? In other words, why would we want to replace a blue site with a red site? Well, the idea was we wanted to get somehow an adjustment. So our simple idea at this point was to take an average of the blue and the red sites in the ward. The point being that we can impute the blue sites from the red ones and also use the raw data for the blue ones and take a weighted average of the two to get a better estimate of what we think might have happened if you'd had a sort of mix of the two types of sites in the blue sites. And then you take the ward average, and then you do this Poisson, the standard sort of Poisson regression analysis to estimate the health effects. So the blue wards are here, the red wards are here. So this emphasizes again the difference between the two types of sites. The blues are much higher than the reds. For the wards now we're talking about. So we can now proceed with the analysis in the two different ways. One would be just to go ahead with the original data and do a risk, an environmental risk health analysis using the Poisson regression. But the other strategy would be to use this weighted average idea of kind of taking the actual values for the blue sites and taking what they would have been had they been in the red group, and then taking an average to get something like something that might be more representative of what actually went on. Fairly crude, but that's the way we've done it so far. So the health effects model is the Poisson regression, as I mentioned. Beta 1 then would be giving you the relative risk of a 1 unit increase in the average of the black smoke. And the short version of the story is in the next slide, that the change in the estimated health risk effect, the relative risk, goes from 7.5% to 8.8%. 7.5 to 8.8%. That's by doing this adjustment that I described. That's not a huge change, but the point about these small risk estimates here and also in the United States is that they're covering a very large population. So a small difference means a lot if you look at it as a percentage of the overall population. So for time, I'll just skip the details on that. You see different results, of course, if you break it down. But anyway, the conclusions are that, it looks like administrators, left to their own devices, will do what they think is sensible and put sites where the pollution is high. And in the United States, it's actually deliberate. They actually try to place the sites where the pollution is high. But if you do that, then I've got the summary here, you overestimate the air pollution levels, the overall levels. You underestimate the adverse health effects, you underestimate them. And then you may be imposing standards, regulatory standards that are too severe because you've underestimated the health effects. This is a big deal. Because as soon as the Environmental Protection Agency in the U.S. announces regulations, it's immediately got lots and lots of lawsuits. by all sorts of people, claiming that this is going to cost too much, right? That's a big issue. And finally, then the number of areas out of attainment will be overestimated. I've put an advertisement to a book which actually has a little bit of this in, and references to a lot of the related work. I don't think that's probably rather rude, but I put it in anyway. And my contact information is there, so if anyone's interested, I can send you copies and stuff. Thank you.
Thank you very much, Jim. I think we have plenty of time for questions if people have issues they'd like to raise. One thing
there's a question there, I think.
Have you used, or have you been able to use the results of this work to try and persuade the regulators to do something that's more sensible from a monitoring point of view?
I've certainly shared it with. I was on one of these Environmental Protection Agency committees that was responsible for the new ozone standards that have just been proclaimed 2014. So I've certainly shared this informally. I've been sort of waiting to actually do the analysis for what happens in the United States to see what it says before going forward with anything more dramatic than that. But I guarantee this is going to have, I might become a highly paid consultant for the oil industry.
One of the questions, you mentioned the fact that there's a tendency to put monitoring sites at high level locations. Partly for legal reasons, is this, or what's the thinking behind that?
Well, I think that in the United States, it's because of the Clean Air Act of 1970 itself, which said that an amazing piece of legislation passed when President Nixon was in power, led to the creation of the EPA. And it stipulates that you have to monitor the air for health effects, in particular, and then secondarily for welfare effects. And so I think the immediate thinking was that, well, if we're really concerned about high levels of the pollution, that's what we should be monitoring, right? And I think it somehow was just groupthink that led to that decision. I think that's how it happened.
Because we get the same in Europe, because any urban area above a certain size has to have monitoring of air quality. And again, we probably tend to get these higher levels recorded because you put them in places you expect pollution to be higher, so that you can prove that no one's exposed to them.
Mm-hmm. Mm-hmm. Okay.
Jane?
Thanks very much, Jim. Great talk. I agree with you, this is very important. I'd love to see this applied to choice of measurements of temperature around the world.
Aha! Yeah, no, you're right. The temperature certainly emerged as a new hazard, and as you may know, there's a World Health Organization project in which Gavin's engaged now that's looking at that very question, and in particular the disease burden around the world due to this. But there we have satellite data and also a chemical transport model data that we can also use to help us figure out whether the sites are represented.
Obviously black smoke pollution is much less important generally than it was, but where I work, the main concerns are pollution from traffic and diesel engines. I was wondering if there's any principles we can learn from that analysis to know how to distribute monitoring stations that monitor nitrous oxides and other particulate matter from diesel engines.
Yeah, so I guess there's the possibility of siting monitors selectively, deliberately to monitor certain things, but it would be
main roads.
Yeah. So that's an example where you'd want to do some site selection, and in fact, for mercury and lead and so on, there are monitors located right next to the sources by law. But for this one, for this approach, it's not so clear whether it would apply, because you really are trying to get these sites at the source. And so you'd really want them to be selective in that sense. So it's a good question. I really don't have a quick answer, really, for it.
Thank you.
It might be slightly related, but I wondered if can you use your model to help inform where would be the most effective place to maintain sites or re-establish sites or remove others like water? Can you use it to inform future monitoring?
Well, there are theories that that we've published which give you an optimal way of siting monitors in such a way as to maximize the amount of information you get about the entire field. So I don't know that you'd want to use this approach for that, but rather you'd want to go back to basics and figure out where to add sites to compensate for this. And there's even an interesting question about whether you would want to cite temporary monitors just to double check on how the other ones are doing. And that's why I thought in the context of citizen science that this might make an interesting project, although there's costs involved obviously and so on, but certainly a big concern to society. So good idea.
Okay, thank you very much.
All
Thank you
right.
very much. Yeah.